Hello, everyone, and welcome back. My name is Jeremiah Wooten with Inspectioneering. And for those that watched our latest webinar with Brian Jack at E2G over CCD and IOW implementation, you know that we ran out of time before we could get to the submitted questions. So I've got Brian back with us today to address some of those questions. Brian, thanks for taking some time to talk to us again. And we're going to kind of run through these. I think we've got probably, 10 or so questions that we wanted to get addressed and knock these out quickly. How you doing?
I'm doing okay.
Good. Well, let's get started. So first question that we wanted to run through is actually from someone in Brazil, fixed equipment mechanical integrity engineer in Brazil. And he asked, what is the best way to determine the time to action in IOW violation cases for both thinning mechanisms and cracking mechanisms? And then the second part, please provide some examples of information IOWs, standard IOWs, and critical IOWs, aside from what's already in API 584.
Yeah, very good. Yeah, so on this first question, I'm going to give an answer and some examples. And in short, I think the answer is not necessarily going to be the type of answer that engineers like. Engineers or inspectors often like hard set rules. If this happens, then you do that. And with this IOW concept, it is significantally not that easy to do in all cases. So there are some IOWs that that are calculations that could provide a remaining life on a component. And an example I'm going to give there is heater tube skin limits. There are well-accepted industry methodologies for calculating remaining life on a heater tube based on the tube skin temperature that it is seeing. And what I've seen and that's a common IOW, tube skin temperature limits on heater tubes. And what I've seen a lot of facilities do is set a couple IOWs for such a limit. They will set a standard limit where if you hit that temperature, you're going to have less than 100,000, or you're going to have 100,000 hours remaining life, which is about 11.4 years. That funny number, 100,000 hours, comes out of API 530. So very industry accepted methodology for calculating heater tubes life. So people set a standard limit around that, but they will set a lot of facilities will also set a critical limit for a much shorter life. I've seen different ranges. Some might do 10 or 20,000 hours. Some might do 3 or 4 months. And then they react to these differently, as you can probably tell by the big difference in the remaining life in those two examples. But that is calculatable. So I can give an example like I talked about during the webinar itself, the crude unit overhead pH, where we talked about an optimum pH range being 5.5 to 6.5. And there, we don't have handy calculations to tell us how much the pipe or exchanger in the overhead, how much longer it's going to last when we get a IOW violation on the low side of that pH. There's no straightforward calculations to do that, like with the creep example. There are some charts and curves that people can go to get some rough estimations of how much faster your corrosion is going to go, but there's not an easy set answer on that. So that time to action is going to be based largely on the experience you have at the facility. Hopefully at the facility, kind of the key triumvirate team that I see that's looking at the IOWs are the unit process engineer, a materials corrosion engineer, and a unit inspector. Ideally, you have experienced people in all three of those positions for each unit. Now, most refineries don't have that. You can still have a successful IOW program if you have at least one and hopefully two of those positions with experienced people. Ideally is 3, but if that number is 0 for you, then it is hard to respond appropriately to IOWs and know how to act on that. Hopefully, maybe you're in a larger refining system, and perhaps maybe you've got some corporate expertise to lean on for that. And if not, then you're probably going to need to look to outside help. But that's hard to do on these are day in, day out programs, so that's very hard to do. So really, to establish an IOW program, you need some good experience in your unit engineer, process engineer, ideally have a materials corrosion engineer, and a experienced unit inspector. So that creep example I gave you, you can calculate numbers, how much longer it's going to last. That enables you to determine how quickly you need to react to that temperature excursion on the heater tube. If you're just barely touching on the 100,000 hour limit, maybe not. Maybe you figure out what's going on. Maybe I got a little bit of coking going on. I'm just going to keep an eye on it. And that's not a big deal. I'll definitely make it to the turnaround when I can look at those tubes and inspect them. If you hit your critical limit, say you've calculated a critical limit that would give you only 3 months life on that tube, then obviously you're going to be reacting much quicker, running that concern up to management, and your actions will be much quicker. Who knows? Maybe you got to take a pit stop, turn around to decoke the foulant in those tubes to get that tube skin temperature back down. Maybe just got to correct some burners. Maybe it's just an issue with the burners. So that one's maybe more straightforward, but that pH example I gave you, again, there's no set easy way to calculate the remaining life based on where you are in pH. A pH 5.4, 5.3, just barely below the target range, is not going to get very many experienced people very excited for immediate action. pH of 4.5, which I've seen many people set as a critical IOW limit, should get the organization acting pretty quickly, very quickly, immediately. So, and I can go on and on with IOW examples like that, but the bulk of them are more like the pH example and not like the creep example. In other words, no hardline calculation is easy. You're going to consult your references. You're going to go for your inspector's experience. You're going to process engineer's experience. The materials corrosion engineers often have a lot of handy charts and tables they can reference to make some guesstimates at corrosion rates, but it's pretty tough to do a hard calculation on something like that. So that's why it's not necessarily the answer that engineers, the very simple answer that engineers like to hear. It's very hard on that timing. It's a lot of things go into it. And when one IOW triggers, like that pH and the crude unit overhead, it's probably going to get you looking at the other IOWs you have in that overhead system. Chlorides and iron are two typical other IOWs you'll have in a crude unit overhead. So, and you got to look at the whole picture, not just the IOW that's triggering. So that's my long answer to that question with a few examples that I hope is of some help.
All right. Well, thanks, Brian. Our second question is from one of our attendees who elected to remain anonymous, who has a question about criticality assessments of IOWs. He asks, how do you normally determine the IOW's criticality? Do you consider the remaining life calculation in your IOW probability assessment where applicable?
Yes. Yeah. So that creep example that I just provided on the first question is a good example of that. And I mentioned that it is common in industry that I've seen in setting IOWs for the heater tubes to have a critical IOW and a standard IOW. Standard IOW have very many years of remaining life, and the critical IOW might be down to months or a year or so. So again, that one's a calculatable one, but many others are not. So just like I said in the first question, the criticality of many IOWs, if not most, are based on industry experience, a lot of industry rules of thumb. The pH targets in that crude unit overhead are industry experience and rules of thumb that have provided successful service in crude unit overheads. So I think I mentioned in the presentation that there should be very few critical IOWs in your program. Most should be standard or a mix, like in the two examples I gave you of having some standard limits and critical limits. So And I think I did mention in the presentation as well that very few IOWs are alarmed, just the critical ones typically, if at all. So again, not the optimum answer maybe for an engineer, but yeah, a lot of experience needs to go into that. Now, API 584, as is mentioned in the question, has provided a good seed list of IOWs you should consider for every major process unit in a refinery. So that's the good seed list. What they specifically are and what exact range you set, and if you decide to set a standard and a critical for those IOWs, tends to be site specific. Yeah, and they can vary from unit to unit. One example on a crude unit I was recently involved with was a chloride IOW we were setting for the overhead. And a typical IOW for chlorides you might see in a crude unit overhead is 20 to 25 ppm maximum. It's kind of optimum. That means you're desalting well and all that sort of thing. But this particular client typically they had some history on their chlorides, and they were typically at 40 to 50 ppm. And they said they were well aware that, hey, that's not ideal, but we've got this water wash up there that's well designed. And despite our high chlorides on the overhead and non-optimum desalting, we are controlling corrosion with our well-designed water wash, which is diluting those chlorides and so forth. So in their viewpoint, they were like, we're not sure we want an IOW or not. I recommended that they still have one as an informational IOW and set it just a little bit higher than what you typically run. I think I recommended 55 or 60 ppm, just so you know that if things are changing, you get some of your in-house experts to look at that and determine why and if that's a big deal. Maybe it's still not going to be a big deal with your water wash. However, most clients on that chloride overhead will set a standard IOW at 20 to 25 ppm. They're desalting well, and they can meet that kind of industry accepted target, and they've decided that sounds like a pretty standard IOW for us. So there can be variability from unit to unit depending on how they're specifically designed. So again, it's getting those experienced core people together to establish the IOW program. Hopefully you have them at the site. If not, hopefully you've got some corporate resources that can assist with that. And if not on that, there are external resources that could assist and take you through that process. But again, no super straightforward way to do that. That's easy cookbook methodology. It's just not going to exist with these IOW programs.
All right, Brian, let's look at the next question from Senior RBI Engineer in the UAE, who asks, where should you start first if a facility does not have either, with IOWs or with CCDs?
Okay, that's a good question, and I'm sure you could get some different opinions on this. But what I have found is that, the CCD, I think, as I described it, it's really documentation of knowledge, capturing in one place for the unit, the documentation of key knowledge around damage mechanisms, great inspection tips, and sort of the key IOWs you need to be looking at for each of the sections of the unit, the corrosion loops or systems as we describe them. I have found that in a lot of sites, that information already exists in this site. It might be a little bit scattered. It's captured in different groups, departments, different file drawers, that sort of stuff, but it's there. It just needs to be put together in that concise format. So given that it's there, if you think it's there, I would start with the IOWs probably. So if you have a feeling you have pretty good knowledge of how you should be inspecting, what your damage mechanisms are, even though you don't have the formal documentation of the CCD, I would proceed with the IOWs because there's a lot of value in the IOW programs. As I mentioned, those sites that have implemented IOWs have a proven track record of reducing process leaks and unplanned shutdowns by being on top of that. So that's where I would go. But I would get both of them done, and you couch it as an either and where to start. Again, I want to emphasize strongly, I would develop those concurrently if you were about to embark on the program. So that to me is the best way to do it. But if you're asked me to pick one or the other to start with, I would say start with the IOWs.
Okay, great. So let's see. We've got another question here from someone in Saudi Arabia, a mechanical integrity engineer, who asks, is it recommended that you set IOW limits during the design phase to help optimize design?
Yes. Yep. I would strongly recommend that. Now, that hasn't been done so well historically with our historical units, but I see it more and more with newer units, which aren't a lot of, but when new units are being done, that is being considered. And it does become very important in determining, for instance, the metallurgy you select for a new process unit. You really do have to know what the intended IOW ranges are for that unit to properly select the metallurgy. You got to know the temperature and partial pressure, hydrogen partial pressure conditions, let you know where you're going to put chrome in on a hydroprocessing unit. In that example I gave in the presentation about reacts, you need to know where your ammonium bisulfide levels are to determine if you can actually get away with using carbon steel or if you really need to use a higher alloy based on the IOW target ranges that they're planning in the operating unit. So yeah, I strongly recommend that the IOWs be developed and considered in the design phase concurrent with the metallurgy selection that you're doing for a new process unit.
Thanks, Brian. So let's see. Next question is going to be from a fixed equipment engineer in Canada. He asks, why are CCDs and IOWs so focused on fixed equipment when things like rotating equipment failures and electrical failures can cause refinery outages too?
Yeah, that's another good question. And it really comes from refiners looking at their in-house statistics. And when they do, they have determined that overwhelmingly it is fixed equipment failures, notably piping, that accounts for most of their process leaks, unplanned downtimes, and significant events. So that's why these IOW programs are highly focused on fixed equipment. It's statistics. One major refiner that I looked at determined that 65 to 70% of their process leaks and significant mechanical integrity events came from piping failures. So a heck of a good place to focus. It's not to say that people haven't, refiners haven't experienced some downtimes or leaks due to rotating equipment failures or instrumentation failures or electrical failures. Those things have happened. And some of the refiners that are well along on implementing their fixed equipment IOWs and CCDs are stepping out and adding some IOWs around those other disciplines. I've seen it most notably with rotating equipment, but some with electrical too. So to me, it is a nothing to ignore, but I would certainly start with the fixed equipment first. And then once you're fairly comfortable with those type of programs, you can progress into the other disciplines.
So now we've got our first question from someone in the US, which is surprising, but this is an operations supervisor in Texas who says he's concerned with information and or alarm overload with IOW programs and wants to know how this can best be mitigated.
Yeah. So, and that's a good question, and I've seen that actually play out. So when the people hit the go button on their IOW programs, I've seen that information overload occur. Some of that should be expected, and people should be expected to need to make some tweaks, especially early on in their implementation of IOWs. That's quite all right. But I also mentioned very few IOWs should be alarmed. Again, IOWs are set around things that, for the most part, are set around parameters that over time can cause accumulated damage and lead to risk. So you don't necessarily need to alarm very many IOWs in your program. So I would avoid, when you're implementing IOWs, really keep that in mind and limit the amount of alarms you set. So that will help take some load off your organization. And then again, on the IOW notifications, depending on the level of the exceedance, the more minor exceedances, I would just send notifications to the core subject matter experts, because they know how best to take the information they're getting. So a small pH excursion down to 5.4, below the 5.5 target, maybe just notify that unit engineer, your materials corrosion engineer, and the unit inspector. None of them are probably going to be all that excited about it, but they might want to be talking about it next time they meet in the hallway, or see if that continues on. They were just a little bit below the pH target. What's going on? Maybe we need to have a chat about that next week. See if there are some things we can do easy to kind of get that back into the optimum target range. Instead of notifying the whole organization. For more critical exceedances, though, as I've mentioned, like a 4.5 pH in that overhead, you do want to broaden out that notification system. Get it in the hands of operations to know that way we need to address this right away, whatever's wrong, because we could start getting into damage rates that are unacceptable. So, and those types of rationalizations do take some time to figure out and play out. But that's how I would start. I would start small with minor exceedances. Again, don't alarm many. With minor exceedances, just notify core SMEs, save the more broader notifications for more significant exceedances, and plan to fine tune as you go.
Okay, next question is from an inspection supervisor in India who asks, how costly is it to implement a CCD and IOW program?
Okay. So let me start with CCDs first. So again, CCDs are just kind of documentation of knowledge. And once you get some of the right people assembled, whether they're in-house or external to help you with that, that is not that onerous or costly a process. IOWs, again, putting them together, putting the IOW tables together is not that difficult for experienced personnel. And you got API 584 to help guide you on the IOWs you should consider for every process unit. That's not much of a problem. Where I've seen some costs come into play is in being able to sample IOWs. And this is a bit of an interesting story. A lot of IOWs are lab samples of either hydrocarbon feeds or refinery process waters, sour waters, looking for things like pH and chlorides and iron and ammonium bisulfide and all the types of things we're pretty familiar with that can cause corrosion problems. And in the old days, if you go back to when I started in refining, I could walk out to a control room and say, hey, I'd like to get a water sample off that sour water boot today. And I'd actually bring a jar. And the operator would walk out with me. We didn't have any H2S detectors in those days. He might have me stand upwind and he'd pour that sour water in a jar, and I'd take that jar into my car and I drive over to the refinery lab and I have it analyzed that day. Piece of cake. It was easy. As time progressed in refining, those kinds of sampling procedures fell out of favor. Let's just say health and safety people didn't like that. And people all got these H2S monitors now, which they track when they buzz off in a facility. So you don't want to do that. So now you need a sample station, a proper sample station. And those sample stations can be expensive. They can be $50,000, $100,000 a pop, and you need a little project to put it together. You need a turnaround often to get it going. So that's one of the biggest slow ups to implementing IOW programs that I've seen. Now, lots of refiners have done that, gone through all that and have all that in place now. But that is one of the more costly things that I've seen. The other thing, as far as cost goes, again, is if you've set up your program and you got this information overload going, and you're trying to have too many meetings to discuss every minor exceedance, or you're telling people to formally reply with some memo on every minor exceedance, those are killers and costly in terms of people's time. Again, as I mentioned in the presentation, you need to have fairly frequent meetings. I recommend quarterly, with RLT leadership present, and they should be efficient meetings to say, where are my risks? Where are the IOWs that are triggering, that are actually presenting me with a risk of not making it to a turnaround or having a process leak or event that I don't really want to deal with. And so you really got to stay focused on that stuff, and to help your people's time management. But as far as monetary cost, again, a lot of people are doing their IOWs and CCDs in-house, so that's your in-house people. If you do it using external consultants, typical costs that I've seen just to get the tables generated and the basic program generated is maybe $30,000 to $50,000 a unit per process unit. I can vary a little bit outside that window, but that's pretty typical for what I've seen, to have IOWs and CCDs assembled for an individual process unit. But the bigger cost, again, is probably getting those sample stations in after you've recommended all these IOWs, because you'll have sample stations needed in most units to properly implement the IOWs. So those are the costs I see around implementing IOW programs.
Okay, we've got a couple more questions to get to. This one's from a corrosion engineer in California who asked, what are some of the major roadblocks to implementing CCD and IOW programs that you've seen?
Okay, yeah, I think I might have covered that a little bit. Yeah, one is the cost of the sample stations and that sort of stuff. Another roadblock is maybe not having all the expertise you need to put together those programs. I mean, not every facility has materials corrosion engineers who seem to be a key centerpiece in putting together these programs for a facility. So kind of lack of resources. And if you don't have those on the site and you don't have corporate support, that can obviously be a roadblock. There are some other ones that are maybe more a little subtle. I talked about the information overload. Some people don't like to see new limits being imposed on their operation. Excuse me, or they look at them as limits. And that's why I tend to not like utilizing the term limit too much when I talk about IOWs, because again, I view them primarily as a communication tool where the subject matter experts are getting information that they need to assess the health of the facility in the proper way. And the payout is, less process leaks, less mechanical integrity events, less unplanned shutdown. So the payout is good, but still, some folks, and sometimes it's sometimes more the management-oriented folks in a facility, get a little off taken by implementation of limits on their process, or how they view them as limits on their process. But so get that out of your mind there. It's a communication tool. It is not atypical to run process units with some consistent, but hopefully just small violation of IOW target ranges. So that is just not unusual and shouldn't be looked at as necessarily a bad thing. Because in the background of all of that, you hopefully, or the intent of the IOW program is you have subject matter experts working on some changes. Maybe they can implement them at the next turnaround to get that IOW back in its target limit. But it doesn't mean that the facility is not safe to operate and you can't proceed. You got the checks and balances in place to make sure that it is. maybe you're doing some extra inspection, but you got some projects initiated to get yourself back into that target range at the next turnaround. Totally very normal activity when you have an IOW program. So, yeah, so I think those are the main roadblocks that I've seen. But I've seen most facilities that are eager to do this, work through all that, and set up good programs.
Okay, thanks, Brian. So this is the last question we're going to get to today. It's from a technical program manager in Louisiana, who asked, how do you measure the success of your CCD or IOW programs?
Okay. Yeah, I'm big into the big bottom line. I think a lot of facilities now have metrics or key performance indicators around process leaks, around unplanned downtimes, or they might call it percent uptime, and certainly significant mechanical integrity events. Facilities track those, corporations track those, and to me, what I've seen with well-implemented IOW CCD programs is those metrics start making good improvements when these programs are implemented. And to me, that's the key. That's really what you're after. So IOWs and CCDs really have nothing to do with inspection compliance or any of that stuff. That's also very important, of course. But what you really want in a refining facilities is minimization of process leaks. Hopefully, no unplanned downtimes. You can run that unit the full turnaround interval to the next scheduled turnaround, and then very much so, you don't want significant mechanical integrity events. So, yeah. So for people that have implemented these programs and done a good job at it, they see those metrics come down. Less unplanned downtimes, less leaks. Little or no significant mechanical integrity events, and that's great success.
All right. Well, that's the last question we're going to get to today. Thanks again, Brian, for taking the time to address some of these questions that were submitted during the webinar. And thank you to everyone for watching and sending in questions. If you have any additional thoughts, questions, concerns, please submit those to our team, and we'll put you in touch with the best person to address those questions. So everybody take care of yourselves and have a great rest of the day.